In this question, he has given the value of damping ratio as 0.5. Now you have got transfer function is 10 into s plus a by s cube plus 9s square plus 18s plus 10a. So if you have cube term, but we know only second order system, s square plus 2 eta omega ns plus omega n square. Now you can write this s cube plus 9s square plus 18s plus 10a by using this. Now multiply the second order system s square plus 2 eta omega ns plus omega n square with s plus b, so that it will be easy to calculate and compare the coefficients given in the transfer function and solve the problem. Among the following, tell me which is the correct answer. Steady state error can be calculated from the system closed loop transfer function for a unity feedback system. As from the unity feedback system, r of s into 1 minus t of s, we can calculate the steady state error. Steady state error can be calculated from the open loop transfer function for a unity feedback system. Yes, we can calculate the Kp, Kv, Ka by using the open loop transfer function. Steady state error is the difference between the input and the output for the prescribed test inputs as time tends to infinity. Yes, this is also a right statement. Many steady state errors in the control system arise from non-linear sources. So in the given options, among the options, as per A's key, 1 and 3 is correct, but as per Ankit Goel sir, it is 1, 2, 3, 4 is right. A's given statement as many steady state errors in control system can arise from non-linear elements, not sources. The open loop transfer function of a unity feedback control system is given as g of s is equals to k into e power minus ts, where k and t are constants and these are greater than 0. He is asking about the stability of a closed loop system. A, which depends upon k, b, both k and t, c, t, d, neither. Characteristic equation, you can write it as 1 plus g of s. You will get e power minus st is equals to minus 1 by k. So s is equals to, you will get it as minus 1 by t ln of minus 1 by k. You can write this logarithm 1 by k, negative 1 by k, you can write it as s is equals to minus 1 by t ln of 1 by k minus 1 by t j power 2n plus 1 into pi. Here ln of 1 by k less than 0 means s is greater than 0, so system is unstable. Ln of 1 by k which is greater than 0, s is less than 0, you can write it as stable system. So it depends only upon the value of k only, it does not depends upon t. In time domain analysis of feedback control systems, which one pair of the following is not correctly matched? Option A, underdamped. Underdamped means eta is less than 1. So oscillations, as we go on upon time, its oscillations gets decreased. So it minimizes the effect of non-linearities. It is correct. Dominant poles. Here he has given transients die out more rapidly, which is wrong. Transients will take more time to die, so it will last longer. Far away from the poles to the left half of his plane, transient die out more rapidly. A pole near to the left of dominant complex poles and near a 0, magnitude is small, magnitude of transient is small. So if a pole exists near the left of a dominant complex pole or a 0, then magnitude of transient is small. Consider the following statement in connection with closed loop poles of feedback control system. Poles on imaginary axis will make the output amplitude neither decaying nor growing in time. Yes, poles on the imaginary axis have a constant amplitude. Dominant closed loop poles occur in the form of complex conjugate pair. Correct. The gain of higher order system is adjusted so that there will exist a pair of complex conjugate closed loop poles on imaginary axis. Wrong. The presence of complex conjugate closed loop poles reduces the effect of dead zones, backlash and Coulomb friction. So if you have a complex conjugate closed loop poles, then there will be absence of non-linearities. None of the poles of linear control system lies in the right half of S-plane. For bounded input, the output of this system is A. Always bounded, B. Could be unbounded, C. Always tends to 0, D. None. As per the ESC 2015 key, the answer should be could be unbounded, because if the poles lie in left half of S-plane, for bounded input, the output will be bounded. If you have simple pole on the imaginary axis, then for it becomes marginally stable, then for bounded input it could be bounded. But if you have repeated poles on the imaginary axis, for bounded input the output could be unbounded. So in question he didn't mention that about the simple pole on imaginary axis or repeated poles on imaginary axis. So if we consider repeated poles on the imaginary axis, it will be unstable. Then for bounded input it could be unbounded. So option B is right according to the ESC 2015 key. Second order position control system has open loop transfer function. G of S is equals to 57.3 K divided by S into S plus 10. He is asking to find the value of K, which results in steady state error of 1 degrees when input shaft rotates at 10 rpm. Now here the game will be around 10 rpm. Now convert this 10 rotations per minute into degrees per second. So to convert 10 rotations per minute into degrees per second, you have to multiply 10 into 1 rotation, you will get 360 degrees out of 60 degrees. So 10 into 60, 360 degrees by 60 degrees. So if you convert 10 rotations per minute, you will get it as 10 into 360 degrees by 60. You will get it as 60 degrees per second. Here R of t is equals to 60 t. It is a type 1 system, so you will find kV. kV is equals to limit s tends to 0 s into g of s. By substituting this, you will get 5.73 k. Now steady state error is given as 1 degrees. So steady state error is equals to 60 by kV. 60 by 5.73 k, which is equals to 1 degrees. You will get k as 10.47. Bounded input, bounded output stability implies asymptotic stability for 1 completely controllable system, 2 completely observable system, uncontrollable system, unobservable system. Which of the above statements are correct? In this question, asymptotic stability means h of t tends to 0 as t tends to infinite, and t tends to infinite, h of t will be 0. And for bounded input, bounded output stability, this implies for completely controllable system and completely observable system. So both 1 and 2 are right.